Welcome back to The Explainer, proudly brought to you by Forge College. We're your go-to hub for mastering Web 3. In our previous lesson, we got our hands dirty with initializing and configuring accounts. But today we are tackling a massive paradigm shift. We're looking at the core contrasts between Ethereum storage and Solana's account model. So if you're coming over from the EVM world, brace yourself, because we're about to unlearn a few deeply ingrained habits about how data is actually owned and stored.
Think of today as our blueprint for moving day. We're going to cover the great storage shift, slots versus accounts, dissecting the account code, the account lifecycle, and finally, translating EVM to SVM. Let's jump right in.
Section 1. The Great Storage Shift. Okay, to really understand this clash, think of it like a major relocation. Ethereum is basically this magical, infinitely expanding house. Whenever you need to store data, you just shove it into a contract storage slot, and boom, the house magically grows to fit it, billing you gas on the fly. But Solana? Solana is way more like a highly regulated facility of rent-controlled storage boxes. You deploy an immutable program account for your code, but then you have to explicitly lease separate data accounts, which are literally fixed-size byte arrays, just to hold the state. You absolutely cannot just shove stuff in there. You need the exact box size and the right key every single time.
Moving on to Section 2, Slots versus Accounts.
Let's dive into this and look at how these two paradigms actually stack up across some crucial dimensions. If you've been writing Solidity, your brain just naturally defaults to implicit 32-byte storage slots that live right inside the contract. But over on the SVM, we think entirely in accounts. On Ethereum, ownership is implicit. The contract just manages its own internal stuff and sizes expand logically. But on Solana, ownership demands an explicit public key that gets checked at runtime. The size is entirely fixed at allocation. And because your programs are just reading raw byte arrays, your serialization format, like using Anchor or Borscht, becomes incredibly important. You literally have to pack and unpack everything yourself.
And that brings us to a really massive gotcha, rent-exemption. Because Solana storage acts like physical real estate on the blockchain, you can't just squat there for free. When you allocate that fixed byte array, you've got to fund it with a minimum balance of lamports. If you maintain that balance, your storage box is rent-exempt and persists forever. But if you don't, well, your box gets evicted and your data is purged, so your data's physical size is directly tied to an upfront financial cost. Next up, Section 3. Dissecting the account code.
Now, what's really cool is seeing how this explicit sizing translates into actual Rust code. Here's a standard Anchor Rust snippet defining a user profile account. That little account macro up top tells Anchor to handle the serialization logic. Let's look at the fields. We've got a pub key for the owner, a string for the username, and a U64 for reputation. Under the hood, a pub key takes up exactly 32 bytes, a U64 takes exactly 8 bytes. But wait, what about that string? Strings are dynamic, right? Well, on Solana, using Anchor, a string requires a specific 4-byte length prefix, followed by whatever actual UTF-8 characters make up the name.
So because we have to pay rent based on the exact size, we actually have to calculate the maximum length of this account before we even create it. It's kind of like doing the math for a moving truck. Let's break it down. The first 8 bytes, that's the Anchor discriminator, a unique identifier Anchor throws in to securely route the account. Then 32 bytes for the owner pub key. Next, those 4 bytes for the string length prefix, followed by, let's say, a maximum of 32 bytes we are reserving for the actual username string itself. And finally, 8 bytes for that U64 reputation score. You absolutely must do this math up front so you can pass the exact required space to the runtime when you create it.
Let's keep rolling with Section 4, the account lifecycle.
Let's trace this whole explicit journey together. Step 1, create and fund. You allocate the space and you pay the rent with lamports. Step 2, initialize. The program verifies it actually owns the account, and then it writes the initial values into that byte array. Step 3, update. This is where you just mutate your memory layout. Step 4, reallocate. Say you need more room? Well, you have to explicitly expand it and pay extra rent. And finally, Step 5, close. You securely wipe the data and reclaim those lamports back to a wallet.
Now, here's a classic headache for EVM developers making the switch. What happens if your user wants to change their name from Bob to a massive 50-character username, but you only reserved 32 bytes? On Ethereum, the dictionary silently expands and it just costs you a tiny bit more gas. But on Solana? No way! Hard fail. The bytes literally aren't there to use. You are forced to execute an explicit reallocation transaction, pass strict program owner checks, and supply more lamports for the extra space. So upfront planning isn't just a best practice here, it is absolutely mandatory.
Let's wrap it all up with Section 5, translating EVM to SVM.
So what's the bottom line for rewiring your EVM brain to the SVM? First, you got to stop thinking about implicit dictionaries. Start treating accounts as explicit, owned byte containers, where ownership is a pub key heavily enforced at runtime. Second, plan your serialization and your sizing upfront. Do that math accurately right from the start to prevent those costly, complex reallocations we just talked about. And third, keep in mind that every single lifecycle action, from creation all the way to closure, carries lamport semantics. Anytime data moves, grows, or dies, lamports are involved for rent, and proper authority checks absolutely must be executed.
I want to leave you with this one guiding principle to keep in your back pocket: designed for explicit allocation and preferred deterministic ownership patterns. If programs are going to control accounts safely, deterministic ownership is the absolute key. And that actually perfectly teases our next lesson, where we're going to dive deep into program-derived addresses, or PDAs, to see exactly how you assign deterministic ownership without even needing private keys. I really hope this blueprint helps you navigate your move from Ethereum to Solana. And hey, as a quick reminder, this explainer was brought to you by Forge College. Be sure to check out forge.college to dive deeper into this topic and explore our comprehensive tracks on all things Web3. Thanks so much for hanging out and learning with me, and I'll catch you in the next one.